we have another recap on angular momentum. There are a lot of questions about angular momentum. It is a pretty interesting and complex topic, but the relationship's simple. Again, angular momentum, P, I guess angular P, equals moment of inertia, I, which is the likelihood or the difficulty for some object to spin, the resistance to basically start spinning, and times angular velocity, which is just the rate at which it's spinning, the number of radians per second, and it is basically the tangential velocity over the radius. And moment of inertia is some form of mr squared, depending on what the shape is. And again, moment of inertia, or momentum, is conserved, so I1 times W1 equals I2 times W2, unless we're exerting external torque into the system. But most of the times we're not, and this is all we pretty much need to know for these problems, which the next one that we'll be looking at is number 25. So pretty simple, but it is a pretty important topic, so we're good. All right, 25, same setup as 24. This one asks about the total angular momentum of the system where there's two satellites. Oh, this got cut off. V2, M2. And so to start it off, we know that the formula for angular momentum, P equals moment of inertia times angular speed. And to start it off, let's start off with satellite 1. We know that the moment of inertia of just we can assume that it's kind of just like a particle rotating about like a sun, is mr squared, this is r1 squared, m1 squared, times the angular speed is v1, is the tangential speed, and to get angular speed we divide by r1 again. So this becomes m1 r1 v1 is the total angular momentum of the first satellite, and we're repeating the same exact process for m2 r2 and v2. We obtain the same result of m2 times r2 times v2, and adding them all up and putting an absolute value sign around them to get the total magnitude of the momentum is answer choice C.